Okay, so our next speaker is Dr. Juan Gómez-Romero from the University of Granada, and he's a research fellow at the Computer Science and Artificial Intelligence Department. He's working in, let me get my notes here. He's a senior research fellow, and his research focuses in machine learning and knowledge representation, and more specifically, he works in the areas of energy efficiency, security, and ambient intelligence. And I think today he's going to say a lot about energy efficiency. So let's welcome Juan.
Okay, let's start from the beginning, not from here. Might be better. Okay, this one is better for a start. And well, first, thank you very much to the organizers of this conference. I'm very happy to be here to to talk about the work that we have been developing in my research group in the last 5 years or so. You will see in the references some names repeated again and again, so I would like to thank them for their hard work, which has made possible to get to this point, and also to open new avenues for research on energy management, in building energy efficiency that we are exploring and that we plan to continue in the future. The starting point of this work is the realization that energy consumption in buildings is a huge problem, or it's a huge issue. Right now, there are several studies which show that buildings account for more than 1/3 of the worldwide energy consumption, and between 30% and 40% is due to non-residential buildings, in which our research is focused, and these amounts are increasing because of the weather change, aging infrastructures, economic growth, and so on. In Europe, there is a directive on energy performance in buildings, which has an objective of an increase of energy efficiency by 30% in 2030. There are several strategies to achieve these energy savings strategies in buildings. Renovation works, that is changing the building. Retrofitting, which is changing, updating, and improving the maintenance of the equipment, mostly the heating, ventilation, and air conditioning system, the HVAC systems, and also using clean energies is the good direction. And also, it has been also shown that improving the operation protocols is very beneficial to improving energy efficiency. That is, selecting the optimal set points, selecting optimal control sequences for the equipment can lead to savings up to 35%. So, currently, these days, this is possible, and this can also benefit from the improvement in the information systems and the IT, which is used in building energy management system. Currently, we have more and more capabilities to collect data, to monitor buildings, and also to remotely control the buildings. So these technologies support new capabilities like data visualization, also advanced analytics for decision making, and also simulation-based control, in which I will focus my presentation afterwards. And well, in this, considering this context, we perform an in-depth review of the historical contributions of data science and machine learning in the area of building energy efficiency. We identified in this review different areas. I will focus on two of them: prediction of building energy load and building operation, because I will come back to them later in the presentation. And regarding prediction of building energy loads, this mostly means the prediction of the amount of energy required at a certain time, and it is directly related to the energy consumption. When we predict energy load, we are predicting energy consumption. Here, weather and building use are the most important factors, and typically the most used techniques have been, like you have here, forecasting from historical data with a statistical time series analysis, classification, and pattern recognition for consumption categories, also anomaly detection, and of course the impact of the building occupants' behavior. Regarding building operation, here we focus on the configuration and operation of the equipment for optimal performance and comfort. Control systems, classical control systems have been prevalent in this area, but this more traditional control is mostly focused on real-time control, which is not the most appropriate in this equipment, particularly for this HVAC, for this heating, ventilation, and air conditioning system, because they have important inertial behavior, and they take a while to start and to get to the optimal performance. So it is necessary to perform longer-term optimization, and therefore traditional control systems, including fuzzy control systems, have been used, but they are not very effective for longer time optimizations. Other techniques like operation rule extraction and also analysis of factors have been used. From our review, we conclude that simple and interpretable techniques have been the most used ones, and indeed we did a more detailed analysis of the date of each paper contribution, and also the features that were available in the main data analysis tools, like R packages or also Python, NIME, and this kind of environments. And we saw a direct correlation between the availability of algorithms and techniques implementing these tools, and also the techniques that have been used in this particular area. So basically, we realized that the most used techniques are those which are available, regardless of if they are the most beneficial or not in this particular case. This situation is changing in the last couple of years, for two reasons. We have all this revolution with the new machine learning techniques, and there are also additional opportunities and challenges derived from the availability of more data because of the progress of the Internet of Things, and also the availability of smart meters. Big data and cloud computing allow us to run software in the cloud with in high-performance clusters and this stuff. And at the same time, there are new regulations, and there are new concerns about privacy and security aspects, which must be taken into account when we perform this kind of data analysis. In particular, the GDPR regulation applies, and also there are some recommendations about data protection, impact assessment for smart grid and smart energy meters. Well, based on these new opportunities, we proposed in another paper a new paradigm for energy distribution and for energy provision to homes. It is called Comfort as a Service, in which we shift the responsibility for achieving energy efficiency from the users to the distribution and to the utility companies. I want to go into details because I would like to show you some results that we obtain by using these more traditional techniques applied to energy efficiency. And afterwards, in the presentation, I will go with new approaches which can leverage the results that we have already obtained. In order to avoid the problem that I mentioned before with real-time control in HVAC system, in the last 10, 15 years, model predictive control has been used in this regard. In model predictive control, we have a simulation model of the building, and we use this simulation model to derive optimal control. Depending on the kind of simulation model that we have available, we can apply some techniques or other. In general, if we have this simulation model, we can solve the control problem as a combinatorial optimization problem. If our simulation model is not very complex, we can solve this by linear programming models, which provide quite good results for small buildings with few interaction between the different components and sections of the building. We can also use a full complexity model that is usually a physical model of the building, which can be built with the usual tools like Energy Plus or other similar software. Also in MATLAB, you can build this kind of models. These full complexity models are more accurate, and they allow the support finding unknown solutions. But usually they cannot be solved numerically, as in the previous case, so we need different approaches. The most typical one is to use stochastic simulation, to use Monte Carlo method, essentially to perform simulation with different expected conditions and with different control strategies, and then select the one which provides better performance and at the same time is compliant to the comfort requirements of the building. When we talk about comfort requirements, in the most basic case, we are talking about temperatures interval. That is, we want to keep the building temperature in a certain range. So here, obviously, we have two different targets. We want to minimize energy, and we want at the same time to keep comfort. And these two objectives are in contradiction. And we explore the use of full complexity models for building control in this project called Energy in Time. It was funded by the 7th Framework Program here in the European Union. And in this project, we partner with different companies and other research groups, including building operators, simulation developers, energy experts, and also we as computer scientists, to develop a control system for HVAC control in non-residential buildings. Essentially, we used a full complexity model, simulating multiple alternative scenarios to select the best one for operating the building, usually in a medium period, like next day or next couple of days. the system integrated the prediction of the expected building conditions, the generation of the control, and also the application of this control instructions. So we cover from deciding the best control strategy to applying this control strategy to the building, which allowed us to test the results of our developments in a simulation environment, but also in a real building. We achieved savings in average about around 20%, and also more in some specific cases. The overall architecture of our system is shown in this picture. We have a corresponding paper, which we hope to will be published very soon. Just to mention a couple of important things, we developed the generation of the control sequence for the building as a Markov process. Essentially, we built a graph of the possible set point changes, the changes in the control instruction for each one of the pieces of equipment as a random graph, and then we perform a random walk on this graph, and well, there was some heuristic information in the generation of this graph, just to adapt to the specific conditions of each building. So here in this part here, we put here quite a lot of heuristic knowledge about the behavior of the building, which, as you may guess, is one of the main difficulties and also limitations for this approach. Then we applied simulation. We simulated the different control strategy, the different plans in terms of the project. For this, we use a cloud-based parallel simulation provided by IES software, which are an Irish company developing simulation models and simulation software. And finally, we modeled the selection problem as a one objective problem with restriction. The objective is minimizing the consumed energy, and the restriction are these temperature comfort intervals that are predefined for each building. And well, we got some interesting results. In particular, we have 4 demo buildings in this project. One of them was the Sanoma Talo building. It's called Sanoma House for the House of Press. It's an office building in Helsinki. Well, as you may guess, with quite extreme weather, particularly in winter. So, well, in simulation, we got some interesting results, and we realized that we could get savings between 13% and 35% in the softer periods of winter. Harsh winter was more difficult to address, well, mostly because the HVAC system is adapted or is optimized for the winter period, so it's working full power during the harsh days of winter. So these results were obtained in the simulation environment. They were quite interesting. Then we proceed to the real building, and we realized 2 things. The first one is that actually the approach works in the real building, but also that most savings are not achieved by optimizing the control strategies that are usually applied by the building operators, but by simply putting a more or less efficient control system on the building. In this chart, you can see that we have some valleys here. These mostly correspond to, well, these 2 charts are testing of the system in the real building. We perform like 1 month of automatic control on the real building, and this is the consumption of our control system, and this is the baseline, the consumption without the control system. I won't go into details on how these figures are calculated, but anyway, you can see that we have some valleys here, which I was mentioned before, and these valleys mostly correspond to weekends. We realize that when operators are out of the buildings, they are not able to manually tune the control for the system, and we can get a lot of savings in these periods. So for this reason, we separated the evaluation between work days and weekend and holidays. As you can see, well, work days go quite well. The actual functioning of the building is close to the simulation model, but usually it performs worse than we had in the simulation model. For weekend and holidays, the savings are huge, mostly for this reason, because it's not possible to fine-tune for the operators the strategies at this point. And well, just to mention that we performed some calculation for the whole year, and we realized that with this control system used a full simulation model without with heuristic knowledge, we can save, well, quite a lot of energy and also contaminant emissions in a whole year. These kind of approaches, and the one that we developed in particular, have some limitations. One of them, the first one, is that creating and running a simulation model is very time consuming. If we want to develop a full complexity physical model of the system, well, this is quite difficult and takes very long to achieve. And also, I have also mentioned, and I have mentioned that heuristic knowledge is required to model, in particular, the distribution function of the Markov process. So this approach is not very scalable, and for this reason, after the end of the project, we started exploring new approaches in which we want to exploit the capabilities of new machine learning technologies to learn the simulation model, and also we can apply machine learning to learn or to implement the decision process based on simulations, or more efficient simulation, and also on historical data. And for this, now we are focused on using deep learning for building energy management. Deep learning can be used mostly in two different ways, which are very closely related to the two areas that I mentioned at the beginning of the presentation, which are simulation and also building control. In the literature, and also I mentioned before that we can find some, sorry, this one before, we can find some approaches using a neural network to predict energy consumption or to predict energy demand. But in general, data-driven simulation requires not only predicting consumption values, but also predicting the state or the next state of sensors inside the building. For example, if we are monitoring temperatures, we need, at the input, we need temperatures and also actuation, control. At the output, we need to predict consumption, but also the next state of these temperature sensors, and maybe new ones which have not been considered at the input. Well, this kind of network architecture is typically a recursive network, which can be modeled in deep learning terms as a recurrent network or also as a sequence-to-sequence network. In this case, we have a sequence of several sequences, series at the input, and we have series or single values at the output. On the left, you can see very recent paper for data-driven simulation using deep learning, and this author are using a recurrent network to get consumption and sensor estimations from the building situation. This approach can be leveraged and in some way to get or to insert into the output sequence not only the expected, the predicted consumption and also temperature values, but also actuation. In some way, the problem, if we have enough historical data to considering good actuation, we can learn not only the next situation of the building, but also the best control strategies leading to this situation. This is directly related to the second approach or the second contribution that we are exploring in this regard, which is the application of deep learning, deep reinforcement learning for creating the control sequences for controlling the building equipment. Well, as you say, reinforcement learning is getting some attention in the last year. There are several successful approaches. Here, what we want is to model the generation of the control sequences as a Markov decision process, in which the possible actions are the set point assignment, and the rewards for these actions are calculated from the energy cost and also from the temperature constraint violations. This is a possible approach to model a reward function for an agent trying to optimize building operation. The purpose in this case is to maximize the accumulative reward, and this can be expressed as optimizing or finding the estimation of the expected reward from the classical Bellman equation. I won't go into details. If you want more information, there are a couple of papers explaining this in more detail. If we focus on deep learning, I will go directly to this second approach. We can solve or we can implement the previous the optimization problem as the estimation of the Q values by using a deep neural network with historical or with simulated data. There are some approaches in this regard, but still they are limited to very specific equipment and also to not to complete buildings in general. And to wrap up the presentation and also just to point out which are the most interesting points in this explanation, I would like to recall that using deep learning for building energy management can solve or can be used to address two limitations that we identified before and that we actually suffered in our project. The first one is the creation and the execution of the simulation model. If we are able to build a data-driven model by using historical data, then we don't have a need for a physical simulation model, and then simulation can run quickly and also without human supervision. There are still two challenges in this sense, because we need to ensure accuracy in the long term, which is currently not achieved by the typical approaches, and also it is important to study how we can transfer models learn in a building to other buildings with different features, but probably with similar equipment. With deep reinforcement learning, we don't need to incorporate heuristic knowledge to model the distribution of this Markov process that we used before to create the control sequence in the building, but there are also some challenges that must be addressed. The first one is, well, the cold start. If we don't have historical data, we need to start the system, and this would imply, well, mostly a learning period in which the functioning of the building wouldn't be optimal. The learning process with deep reinforcement learning has, in some cases, has some stability problems because, well, it's not easy to figure out the best control strategies in these cases. And of course, and it has been mentioned in a different context, but it is also important in this case, interpretability, because it is useful and also necessary in most cases to make the building operators part of the decision process when they manage the building. Not only because they have the responsibility for the outcomes of the system, but also because they have very valuable experience, which sometimes is not included in it cannot be included or cannot figure out by the automatic processes. Right now, we are just starting this project funded by the Spanish Ministry of Science and Universities, and also with the collaboration of IES, developers of situation models, and Google Cloud. They are providing support for running our machine learning algorithms on the cloud. So if you have more questions, or if you are interested in this kind of research, we are very open to collaborations. That's everything from me. I will be pleased to answer any question or any comment that you may have.
Okay, let's thank Juan for that very So any questions?
Thanks. I have a question. So when you use deep reinforcement learning, is the algorithm trained in a simulator or in the real world environment?
We have started with a simulation model. Actually, right now we have started with one very simple simulation model, which has been wrapped into this kind of OpenAI gym environments, and we are using this for our first test. Now we are trying to integrate a full complexity simulation model like the ones provided by IES in the environment. And then when we are more or less confident with the process, we want to test this first in the lab and then in the real building. So the real building is like the last step of this in our methodology. We expect to do well, I hope that in 1 year or so we will be able to put some of this in the building.
Then, so as a follow-up, so if you train in the simulator, right?
Yeah.
How do you deal with the kind of the transfer or do the domain adaptation? That when you train your algorithm in the simulator, but you will eventually develop it in the real world. But there is always a gap between the.
Sure.
So how is there any consideration to deal with this?
So far, we are actually that's a good question, and this is why we are very happy to have with us this company IES, because they can provide a simulation model very close to the real functioning of the building. Actually, they created simulation models for the pilot buildings in the Energy in Time project for this San Matalo building, and they reported an accuracy about 5% deviation from the real functioning of the building, which is very useful to reduce the gap between going from the simulation model to the real building.
So the general vision is to reduce the gap.
Yeah. Yeah, this is actually one of the main contributions of this first project. Not going to the building, but reducing the gap from the lab to the building.
Okay, any more questions? I guess I have a question. Have any studies been done on improving the efficiency of human behavior and how that affects energy efficiency? For instance, people turn off lights when they're not in the same room, or turn off their air conditioner when they're not home, or shut the window.
That's crucial. I mean, in our work, we didn't focus very much on this, but we had a very interesting experience. We focus mostly on non-residential buildings, in which the capabilities for the occupants, well, are reduced, so to speak. But one of our demo buildings was a hotel in Levi. It's north of Finland, very extreme weather there. And there, the occupants do have the capability to open windows, to change things, and we got the worst results in the project for this building, because actually it is very important to incorporate into the optimization process the uncertainties that are, let's call them uncertainties, that are produced by the behavior of the occupants. There was, at the time that we are developing Energy in Time, there was another project specifically focused on what they call energy awareness or something like this, which is these guys applied game theory and also gamification to improve the behavior of the users in the building. And they realized that just putting a screen with the current situation of the building and also the energy saved was enough to get like 10 or 15% of savings in a building without any other additional measure. So it was very interesting.
Can I answer your question?
Well, sure, but
In our institute, we make a calculation in order to decide whether it is worth to switch off the light in the toilet. And it came out that the best thing that we could do is to tell people switch off the light, because doing that automatically costs us 30 years of energy saving in the toilet. So by buying the equipment, and not to say about construction of the equipment.
Okay, more questions. All right, then let's thank Juan again for a fascinating presentation.